All right, honors chemistry people, it is time for us to do our review. I have put a review assignment on for today's Canvas module. I just wanted to talk about all the things that I'm expecting you guys to know, okay? So this exam is going to go from chapter 3, atoms. So you need to know all the different philosophers and the scientists and the different atomic models that they proposed. I did throw in an extra scientist for you to know that is not in your notes. You're going to want to look up Joseph Proust. He is a French scientist about a little bit after the time of Antoine Lavoisier, who came up with the law of definite proportions. So take a look at that law and Joseph Proust and add him to your repertoire. Okay? So you're going to want to know about Democritus and Aristotle and Empedocles and their different philosophies. And you're going to want to know why Aristotle and Empedocles' idea came forth and was more accepted than Democritus. Okay. Wow. I don't want this big. We want to talk about Sir Robert Boyle and Sir Isaac Newton, Antoine Lavoisier as well. And in between Antoine Lavoisier, we want to put in Joseph Proust. Some places spell it like this. Okay, so look up Joseph Proust and look up the law of definite proportions. Okay, that's an important law that goes along with Dalton's theories as well. Okay, and then we want to know about Dalton, and we want to know Dalton's model of the atom with the billiard ball. Okay, we want to know about J.J. Thomson and his discovery of the electron and how he did it with a cathode ray tube. We want to know that Robert Millikan was the one who actually figured out how much an electron was charged and how much an electron weighed. We want to talk about Thomson's model again. This is Thomson's model, but this is not what, this right here is not what Thomson did. This was Rutherford. Okay. So Rutherford discovered the proton. He also discovered the mass of the proton. So I need to rearrange my notes there a little bit. We want to talk about Rutherford and the gold foil experiment and how that came up with the idea of the nucleus and how he did that. We want to talk about James Chadwick coming up with the neutrons. We want to talk about isotopes and what an isotope is. Remember, an isotope is an atom that has the same number of protons but different number of neutrons. So it's the same element, it just has a different mass because of the protons, or because of the neutrons. Sorry, I misspoke, because of the neutrons. So I also want you to know how to read atomic block squares with the name, the atomic mass, the protons, or the atomic number, and the symbol. Okay? I want you to know how to find an average atomic mass. I want you to be able to find protons, neutrons, and electrons in an atom if I give you the mass or whatever combination of numbers. Okay? I want you to know the properties and locations of subatomic particles. Okay? So you need to know that. You need to be able to calculate an average atomic mass. And here's another example of an average atomic mass calculation. You need to be able to do different isotopes. And there's 2 different charts of isotopes and how you do them. Okay, our next thing, you need to do moles. You need to be able to convert grams to moles, to atoms, to molecules, and back and forth. Okay, So you need to be able to use Avogadro's number. You need to be able to use the periodic table to determine what the molecular mass is, or the molar mass. Okay. You also need to be able to use the periodic table to find the molar mass of a compound, not just an element. Remember, compounds, we just add up all the elements together. Remember, we are doing masses from the periodic table to the nearest hundredth. Okay, so the 100th spot is where we are rounding. Okay, a lot of you guys are hung up on that. All right, you need to be able to do these conversions, grams to moles, moles to grams, atoms, molecules, any combination of those. You also need to be able to do those calculations with the correct number of significant figures. Okay, so I will be watching sig figs on this. I will be watching conversions. I will be watching unit analysis and all of that. Okay, any questions so far? Hopefully this is all pretty old hat. Okay, so molar conversions using molecular masses, using unit analysis. There's some examples here. So go through the videos that go through these examples. Okay. It looks like I didn't do all of the examples for you. And then last but not least, we're going to be doing nuclear chemistry on this exam as well. So I want you to know that nuclear chemistry has much more energy associated with it than chemical chemistry. I want you to know that fusion even has more energy associated with than fission. Okay. I want you to know what ionizing radiation does and what it is. I want you to know Rutherford's experiment with alpha, beta, and gamma and how he was able to differentiate those. I want you to know penetrating power of alpha, beta, and gamma and how dangerous they are. Okay. I want you to be able to balance equations using alpha and beta equations. Okay. And using your conservation of mass with protons and neutrons and mass numbers, and being able to use the periodic table to determine what nuclide that decay has turned into for the daughter nuclide. Okay, so any of these balancing equations, remember, let's just do a quick example. I started with plutonium-238. 238 is the top number, that is our mass number. I do the bottom number from the periodic table, that is the number of protons in plutonium. And if I have an alpha decay, I'm going to write an alpha particle, or I could write it like this. And remember, 238 is equal to 4 plus 234. So remember, both sides of the equations have to add up to the same. We have conservation of mass. So 238 needs to equal 4 plus 234. And 94 needs to equal 2 plus 92. And then we look from 92, we look on the periodic table with the number of protons to find that that is indeed uranium. Okay, so you need to be able to balance both alpha and beta particles decay equations. You need to tell me the difference between alpha and beta. Okay, I want you to be able to also talk about the band of stability. Okay, we did not go over positron or emissions. Okay, I want you to talk about the band of stability and why we have to have neutrons in that atom to make things stable. It has to do with the strong nuclear force and how it interacts with the gluons in there. Notice we have a ratio of between 1.1 and 1.5. So 1.1 to 1 neutron or 1.5 neutron to 1 proton in there is stable. Remember these black squares in here are the stable isotopes. The isotopes that aren't stable are either the blue here, they're going to decay with beta emission. The orange here, they're going to decay with beta plus emission. Okay, the red here is a proton, and the purple here is neutron. And alpha doesn't really start until we get into some pretty heavy elements. Okay, and fission only happens for a few elements up here. Okay, now remember, our last stable element is lead. Anything larger than lead at 82 is too heavy to be stable, regardless of the ratio between protons and neutrons. Okay, so once again, our stability ratios here and what it takes to be stable. Okay, we talk about binding energy, where we will fuse. We will use fusion up until lead, or not lead, up until iron, and we will use fission on the heavier end of the isotopes, okay, to get energy. Okay, then I talked about a radioactive decay series and how half-lives are different. When we have big isotopes, big elements, it has a whole series of decays that it has to go through to be able to get to a stable isotope. Now, some of those decay processes happen really quickly. Some of them take a long time, and it really depends on how far that isotope is from that band of stability. The farther out that isotope is from the band of stability, the faster that half-life is. The closer that isotope is to the band of stability, the slower that half-life is. Okay? We talked about radioactive dating. We talked about half-life and what it takes for things to go. We did several problems using half-life. So you need to be able to calculate half-life problems, calculate how much is left, calculate how long a half-life is, calculate how many half-lives have undergone. Okay, so there's a bunch of example questions as well. We talked about how we use carbon dating to date anthropological sites using the half-life of carbon-14. We did some mathematical problems to show you how it's done. Okay. And then we talked about different half-lives. I gave you a couple of different equations that you could use. You could also figure it out the long way if you don't want to use the equations. We talked about, just for fun, the Shroud of Turin and how when they did the half-life dating on the Shroud of Turin, they dated the Shroud of Turin to the Crusades and not to the original time that Christ was purported to live on the earth. And that's where we left off. So these are all the concepts that you need to know for the exam. The review should go over all of these concepts and give you a fairly good idea of what you will see on the exam. The exam will be Monday, next week Monday, when we come back from UEA break. So be studying. I don't want you to study the whole break. Do use the break, but make sure that you come back studied and ready for this exam. We'll see you later. Bye.